Something just tore through our solar system at 137,000 miles per hour. Not a meteor, not a stray asteroid, something that shouldn't now exist here at all. On July 1st, 2025, telescopes in Chile caught a faint dot moving wrong. Too fast, too straight. When they traced its path backwards, the numbers broke every rule. This thing came from outside, way outside. From somewhere between the stars, it had been traveling for billions of years before our sun even knew we existed. This is 3I/Atlas, the third visitor from interstellar space ever detected, and its path through our solar system is telling us something that changes everything we thought we knew about what our TMs out there in the dark. If you value documented space science like this, subscribe our TMs, the best way to support our work. Also, comment from which city, US TM, are I hearing this from. This script is researched and factual, using sources from NASA and the European Southern Observatory. Now, back to the story. The Atlas telescope at Rio Hurtado spotted it first. Magnitude 18, barely visible, moving through Serpens Cauda constellation near the galactic center, but within hours, something was clearly wrong with the math. The object was designated A11PL3Z, temporary name for a temporary visitor. Except this visitor was moving at 61 kilometers per second relative to our sun. For context, the fastest human-made object ever built, Parker Solar Probe, maxes out at 200 kilometers per second when diving toward the sun with gravitational assist. This thing was doing 61 kilometers per second in the cold vacuum between stars. The numbers kept getting stranger. Its orbital eccentricity measured 6.141. Any object with eccentricity above 1 is unbound from our sun TM's gravity. Jupiter can kick a comet up to about 1.05 at most. The previous interstellar visitors, 1I/Oumuamua and 2I/Borisov, clocked in at 1.2 and 3.4 respectively. 3I/Atlas hit 6.141. The highest eccentricity ever recorded in our solar system. Its trajectory looked like a straight line, not the curved path of something falling toward the sun, but the track of an object that happened to be passing through and didn't plan to stick around. When astronomers traced its path into the past, they found it came from the general direction of Sagittarius, the center of our galaxy, the thick disk where ancient stars orbit in tilted paths above and below the galactic plane. Pre-discovery images stretched back to June 14th. The Zwicky Transient Facility at Palomar had been tracking it without knowing what it was. So had Atlas telescopes around the world. All the data pointed to the same impossible conclusion. This object had been drifting through interstellar space for somewhere between 3 billion and 11 billion years. It was older than most stars in our neighborhood, maybe older than our solar system itself, but the real shock came when they got a good look at it. Hubble locked onto the target on July 21st, 277 million miles from Earth. The image showed something no one expected, a teardrop-shaped cocoon of dust and gas, a bright nucleus wrapped in a massive coma stretching for thousands of miles. This was Oumuamua TMT, a dead rock tumbling through space. This was an active comet, ice turning to vapor, dust streaming away in solar wind. The James Webb Space Telescope confirmed it. Carbon dioxide, water vapor, carbon monoxide, classic comet chemistry. The Swift Observatory detected hydroxyl radicals in water. The Very Large Telescope in Chile found cyanide gas and atomic nickel vapor on August 14th and July 20th, respectively. Every signature matched what Oumuamua TM'd expect from a comet. But this comet had been frozen solid in the space between stars for billions of years. Now, as it approached our sun for the first and only time, it was waking up. The nucleus itself appeared small through Hubble TM's eye, no bigger than 5.5 kilometers across. But estimates of the full object with its coma ranged up to 15 miles wide, 100 times larger than Oumuamua, 10 times bigger than Borisov, and it was moving faster than either of them, a bullet train of ancient ice screaming through our cosmic neighborhood. But here, TM's where it gets weird. The coma had a tail pointing toward the sun, not away from it. Solar radiation pressure should blow comet tails away from the sun, always, but 3I/Atlas was ejecting material so heavy that radiation couldn't have TM'd push it. Massive particles continuing forward on momentum alone, like a cosmic shotgun blast aimed straight at our star. The path itself defied probability. Most interstellar objects should come from random directions. But 3I/Atlas was traveling almost perfectly aligned with the plane of our solar system. Its trajectory tilted just 5 degrees from the ecliptic, the orbital plane where all our planets live. Harvard astrophysicist Avi Loeb calculated the odds of this alignment occurring naturally. 0.2%, less than 1 chance in 500. Some speculated about artificial origins, the size, the trajectory, the apparent lack of detectable chemistry early on. But as the object warmed and outgassed, every measurement screamed comet, real ice, real rock. Real chemistry from a real star system somewhere in the thick disk of the Milky Way, which raises the bigger question, where did it come from? The velocity components tell the story. When 3I/Atlas arrived at our solar system, it was moving away from the galactic center at 51 kilometers per second. It was also moving upward through the galactic plane at 18.5 kilometers per second. That vertical component is huge compared to nearby stars. It means this object follows a highly tilted orbit around the galaxy, the kind of orbit typical of thick disk objects, ancient stars and debris from the early days of the Milky Way. The thick disk is where the galaxy keeps its oldest material. Stars with lower heavy element content than our Sun. Planetary systems that formed when the universe was younger and different. If 3I/Atlas came from there, it carries chemistry from a star system that may have formed 7 billion years ago or more, when our Sun was nothing but a cloud of gas that hadn't an OTM started contracting yet. October 30th, 2025, perihelion, 3I/Atlas will reach its closest approach to the Sun at 1.4 astronomical units, just inside the orbit of Mars, moving at 68 kilometers per second, maximum speed. Then it begins the long journey back to interstellar space, never to return. Mars will get a front row seat. On October 3rd, the comet passes within 29 million kilometers of the red planet, close enough for the Mars Reconnaissance Orbiter to image it with high-rise camera at 30-kilometer resolution. The first detailed photographs of an interstellar visitor from another spacecraft, Earth will have to settle for distance viewing. The closest approach to our planet comes in December, when 3I/Atlas is already heading back out. 1.6 astronomical units, about 150 million miles. Far enough to be safe, close enough to keep watching. But by then, the real show will be over. Through September 2025, since ground-based telescopes can track it, then it passes too close to the Sun to observe safely. It reappears on the other side in early December, but by then it'll told TMs already accelerating away. Soon it will be too faint to detect. Another dot of light fading into the cosmic background, except for what it leaves behind. Data, chemistry, proof that the space between stars is now TM to empty, proof that objects can survive billion-year journeys through the galaxy and still tell stories about where they came from, proof that other star systems eject material just like ours does, and that material eventually finds its way to places like here. The Vera C. Rubin Observatory came online this summer. Its wide-field survey should detect 1 or 2 new interstellar objects per year, which means 3I/Atlas will not TM today be the last visitor, just the most extreme one so far, the fastest, the oldest, the most eccentric, and probably not the weirdest. Colin Snodgrass at the University of Edinburgh leads the European Space Agency's Comet Interceptor mission. Scheduled for launch in 2028, the spacecraft will wait at the L2 Lagrange point until a suitable target appears, then deploy 3 smaller probes to intercept and study a comet up close. If another interstellar visitor arrives with enough advance warning, Comet Interceptor could provide the first detailed analysis of material from another star system. But most interstellar objects will remain distant targets for ground-based telescopes, too fast to intercept, too faint to study in detail. 3I/Atlas represents a rare opportunity. Large enough to observe clearly, active enough to produce detectable spectral signatures, on a trajectory that brings it close enough to Mars for spacecraft observations. The next comparable opportunity might not come for decades or centuries. Most interstellar objects are probably much smaller than 3I/Atlas, dark, inactive, undetectable until they're already leaving the solar system. We got lucky with this one, and the most revealing. But 3I/Atlas holds darker secrets. The object's extreme velocity suggests a violent ejection from its home system. Normal planetary formation doesn't produce objects moving at 58 kilometers per second relative to their local stellar environment. Something catastrophic had to happen. A close stellar encounter that disrupted the entire system, a supernova explosion that blasted material across interstellar space, or the death throes of a massive star that went hypernova and scattered planetary debris throughout the galaxy. The age estimates support this violent origin story. 11 billion years puts 3I/Atlas near the formation epoch of the Milky Way itself, back when galaxy mergers were common, when massive stars lived fast and died young in spectacular explosions, when the interstellar medium was a shooting gallery of high-velocity debris from stellar catastrophes. If 3I/Atlas really is that old, it survived the most violent period in galactic history. It witnessed the heavy element enrichment of the galaxy as successive generations of massive stars exploded and seeded space with carbon, oxygen, silicon, and iron. It may have passed through multiple spiral arms as the galaxy settled into its current structure. It certainly survived gravitational encounters with countless other stars during its billion-year journey to our solar system. The survival itself is remarkable. Most small objects get disrupted by tidal forces during close stellar encounters. They fragment into rubble piles or get completely destroyed. But 3I/Atlas remained intact enough to survive billions of years in the hostile environment of interstellar space. That suggests either exceptional structural strength or incredible luck, or both. The rotation data provides clues about internal structure. The 20% brightness variation over several hours indicates an elongated shape, not spherical, probably twice as long as it is wide, similar to many comets in our solar system, but unusual for an object that supposedly survived billion-year bombardment by cosmic rays and micrometeorites. Most interstellar objects should be heavily weathered, their surfaces sand-blasted smooth by high-velocity dust impacts, their volatile materials depleted by cosmic ray heating. But 3I/Atlas shows fresh cometary activity, clean spectral signatures of water, carbon dioxide, and organic compounds, like it was somehow protected during its journey through space. Maybe it spent most of those billions of years in a dormant state, frozen solid at temperatures near absolute zero, with surface volatile materials locked away beneath protective layers of non-volatile rock and dust, only awakening when solar heating penetrated deep enough to reach the subsurface ice deposits. The outgassing patterns support this interpretation. Early observations showed little activity when 3I/Atlas was still 4 astronomical units from the Sun, but as it moved inside 3 astronomical units, the coma brightened dramatically. Water vapor production increased exponentially. Like ice deposits buried beneath the surface were finally reaching sublimation temperature. This delayed onset of activity is characteristic of ancient comets with heavily processed surfaces. New comets from the Oort cloud start outgassing much farther from the Sun. Their surface ice is fresh and easily sublimated, but comets that have made multiple passes through the inner solar system develop protective crusts that inhibit outgassing until solar heating becomes intense. 3I/Atlas displays this old comet behavior despite being on its first pass through any stellar system in billions of years, which suggests its surface was already heavily processed before it ever encountered our Sun. Cosmic ray bombardment and micrometeorite impacts had created a protective lag deposit that kept the interior ice pristine, while the surface evolved into a non-volatile shield. The chemistry tells a complementary story. The water vapor detected by JWST and Swift Observatory shows isotopic ratios different from Earth's oceans, different from comets in our solar system. The deuterium to hydrogen ratio is elevated, suggesting formation in a colder environment with different stellar chemistry than our Sun's natal nebula. Carbon monoxide ratios are also anomalous, higher than typical solar system comets, but lower than interstellar ice detected in molecular clouds. Like 3I/Atlas formed in an intermediate environment. Maybe the outer reaches of another star system where stellar heating was minimal but not completely absent. The nickel detection is particularly intriguing. Atomic nickel vapor is rare in comets. It requires high temperatures to vaporize metallic nickel from solid grains. Most comets don't get hot enough during normal outgassing to produce detectable nickel lines. But 3I/Atlas was generating strong nickel signals even when it was still relatively far from the Sun. This suggests either unusual composition or unusual heating mechanisms. Maybe the nucleus contains more metallic material than typical comets, nickel-iron grains incorporated during formation in a metal-rich stellar environment. Or maybe the rapid rotation and tidal stresses from our Sun's gravity are generating internal heating through friction and flexing. The forward-pointing tail adds another layer of mystery. Normal comets develop tails that point away from the Sun because solar radiation pressure pushes small dust particles outward. But 3I/Atlas was ejecting material too heavy for radiation pressure to affect large grains or chunks of ice that continued forward on ballistic trajectories. This heavy particle ejection suggests violent outgassing events, not the gentle sublimation typical of most comets, but explosive decompression as subsurface ice pockets suddenly reached vapor pressure, like underground chambers of pressurized gas suddenly venting through surface fractures. The explosive outgassing could explain the unusual dust production rates. Hubble detected dust loss consistent with comets much closer to the Sun, but 3I/Atlas was producing that much dust while still at Mars distance. Either it's much more active than normal comets, or it's ejecting larger particles that carry more mass per unit area. Both interpretations point to internal processes unlike anything in our solar system. Maybe billions of years of cosmic ray bombardment had created subsurface chemistry that becomes unstable when heated. Radiolysis products that decompose explosively when they reach certain temperatures. Exotic ice phases that undergo rapid phase transitions under solar heating. Or maybe the nucleus structure itself is unusual, instead of a solid monolithic body. 3. I/Atlas might be a loosely bound collection of smaller fragments, a rubble pile held together by weak gravity and surface ice cementing. When solar heating weakens the ice matrix, entire sections could break away and vaporize rapidly. The brightness variations support the rubble pile hypothesis. A solid rotating body should show smooth periodic changes in brightness, but 3 I/Atlas displays irregular fluctuations superimposed on the main rotation signal. Like pieces of the surface are constantly changing as material gets ejected and internal structure rearranges. This dynamic evolution makes 3 I/Atlas particularly valuable for understanding interstellar object physics. We're watching in real time as an ancient relic from another star system responds to solar heating for the first time in billions of years. Every observation reveals new details about how these objects survive their journey through the galaxy, and what happens when they finally encounter stellar radiation again. The timing is fortuitous. Advanced space telescopes like JWST and Hubble provide unprecedented spectroscopic capabilities. Ground-based observatories have better sensitivity and resolution than ever before. We're studying 3 I/Atlas with instruments that didn't exist when the previous interstellar visitors passed through, but the observing window is finite. After December 2025, 3 I/Atlas will be too faint for detailed spectroscopy. The chemistry will remain locked in the data archives. Future visitors might be smaller, darker, less active. We may not get another opportunity like this for decades. In 2026, archaeologists working at a radio telescope site in Chile will uncover foundation stones marked with precise coordinates. Not for any earthly location, but for a point in space where 3 I/Atlas first entered our solar system, July 1st, 2025. 4.5 astronomical units from the Sun, the exact spot where humanity got its clearest look yet at the chemistry of another star system. The first confirmed comet from the thick disk of the galaxy, proof that the universe has been building and breaking and rebuilding worlds for longer than we ever imagined. Cold math, ancient ice, billion-year journeys.